All right, people, welcome back. We've got a good one today. This is the first of our sort of big main theorems from chapter 16, and it is called the fundamental theorem of line integrals. You might recognize the first bit of this name as coming from the fundamental theorem of calculus, and it is no coincidence. We will see this in a second, but first let's start with a sort of motivating example to get us situated with what's going on here with this fundamental theorem of line integrals. So let's recall what is, at the sort of current moment, our favorite vector field on the plane. This one, f of xy, equals to minus y in the first component and x in the second component. This one that kind of swirls around the origin in circles. So let's consider two curves, C1 and C2. And the parameterization for C1 will be this function R1 of t that is cosine of t in the first component and sine of t in the second component, where t varies from 0 to pi. Note that this traces out the top arc of the unit circle, right? And this second curve, R2 of t, in its first component, we'll have 1 minus 2t, and in the second component will be constant equal to 0. So this one is going to parameterize a straight line segment, right? We have something linear in the first component. So this first one, like we said before, is the circular arc joining the points 1, 0 and negative 1, 0 in the xy plane. And the second curve is just the straight line segment joining those same 2 points. So notice if you start here at t equals 0, you'll have the point 1, 0, and at t equals 1, you'll have the point negative 1, 0. So we have 2 different curves between the same endpoints, okay? And so for a bonus homework, you can compute the line integral of this vector field f along these 2 respective curves, and you'll see that the line integral of f along the first curve is pi, and the line integral of f along the second curve is 0. Okay? So what are we to make of this information? Well, perhaps you were expecting that the 2 line integrals would not be the same. I mean, I think it's probably not surprising that if we have 2 different curves, that the line integrals of some vector field along those 2 completely different curves are not bound to be the same number at the end, right? Even if those 2 curves have the same endpoints. Because generally, the vectors from the vector field along those curves could be totally different. It's in 2 really different regions of the plane that you trace along those curves. To just end at the same place seems like it's not really enough to have that the line integrals are the same. However, if your vector field big F that you start with is conservative, which means that it is equal to the gradient of some scalar valued function, little f, then we do get something nice here. So the fundamental theorem of line integrals states exactly that. It says that if the vector field big F that we start with is the gradient of some scalar valued function, little f, and if our curve C is parameterized by some function whose parameters start at A and end at B, then the line integral of the vector field big F along C equals to the difference of the function evaluated at the endpoints of the curve. So we'll take f of the ending point of the curve minus f of the starting point of the curve. Notice how much this looks like the fundamental theorem of calculus, right? We could say here, we could even replace big F in this part of the statement with the gradient of little f. In our experience here, the gradient represents some kind of sort of multivariable derivative, right? And so then it would kind of look like the fundamental theorem of calculus, that the integral of the derivative of some function little f equals to that function little f evaluated at the endpoints of the place along which you're integrating. Okay, So what can we say? What does this, like, let's kind of like put it in prose or something. So what this means is that if our vector field big F is conservative, then the line integral of big F along any curve only depends on the endpoints of that curve. So you just evaluate the function, little f, the potential function, at those two endpoints and take the difference. And so let's prove this one because it's a pretty fun proof. So let's let our curve, r of t, be equal to x of t in the first component and y of t in the second component, where t goes from a to b. And so then let's compute the line integral of the gradient of little f is going to be given by the actual integral from a to b of the dot product of the gradient of f evaluated at r, dot product with the tangent vectors to the curve r prime of t. Okay? And this is just from the sort of definition of line integral that we met in, I believe, the previous talk. So, let's compute what this is, though. Let's remind ourselves, what is the gradient of this function little f? Well, it's got, in this case, two components. The first one is the partial derivative of little f with respect to x, which we'll evaluate at little r of t. And the second is the partial derivative of f with respect to y, evaluated at r of t. And we could write, we could write these tangent vectors, r prime of t, as, well, if we know r prime, or r of t is x of t in the first component and y of t in the second component, then those tangent vectors are given by the derivatives of x and y with respect to t in their respective components. So the first component's dx dt, the second component's dy dt. And so now we have this here dot product. So let's see what that is. Let's do it. So we'll have the partial derivative of f with respect to x at r of t times dx dt plus the partial derivative of f with respect to y at r of t times dy dt. Right? So if you recall, though, this dot product looking expression, which I guess it is this dot product from above, but this expression really is the section 14.5 chain rule applied to the function little f of r of t. It's a one variable function, right? So this really is, in its essence, is the derivative with respect to t of this scalar valued function of the single variable little t. So we can write it as, now our expression is the integral from a to b of the derivative with respect to t of little f of r of t, and we're integrating with respect to t. But expressions like this are exactly expressions like the fundamental theorem of calculus. In particular, the fundamental theorem of calculus tells us that this integral is equal to little f of r of b minus little f of r of a. You just evaluate the function at the endpoints and take the difference. And so this proves for us the fundamental theorem of line integrals. Now, I will say that the case that we showed here was just for the case of a vector field in the plane. We could have done a vector field in space or even a vector field in any dimension, say r to the n. We would just have more components here and more components here and more components here. And so in order to save space, I just did the two-dimensional one because the higher dimensional ones are no different in effect. So there you have it. So let's do an example. So like I just said, we can do this when we have a vector field on R3. So let's do an example in R3. So we'll have big F of x, y, z equals to 2x cosine y in the first component, minus x squared sine of y plus z in the second component, and y in the last component. Now we saw this one in example 2 of section 16.1. So I think we determined there that this was a conservative vector field, and the potential function for it, little f, was given by little f of x, y, z equals to x squared times cosine of y plus z times y. So if c is any curve that starts at this point that I picked here, 1 pi 0, and ends at this other point that I picked out of thin air here, 1 pi over 2, 1, then the fundamental theorem of line integrals tells us that the line integral of big F along C is just as easy as evaluating this function, little f, at these two endpoints and taking the difference. And so what do we get there? Little f of 1 pi over 2, 1 is, let's see, 1 times 0 plus 1 times pi over 2. So that gives us pi over 2. Good. And little f of 1 pi 0 is minus 1 plus 0. So just minus 1. So then we have here pi over 2 minus minus 1 is pi over 2 plus 1. All right, so that's any curve. See, so we could have specified some particular curve to try to throw you off or something like that. So that would probably be how you'd see it in the homework or something. If you can determine that the vector field big F is conservative, then you can forget whatever weird curve they give you and just focus on its endpoints. So that's very clever. So join us in the next talk. We'll talk about some fun consequences of this fundamental theorem of line integrals. We'll see you then.